Hello, this is a video on Descartes' rule of signs and the rational root theorem. The last couple videos have been on polynomial functions and the fundamental theorem of algebra, and we're going to be trying to find zeros of a polynomial. So let's consider this big long polynomial here, which is a 7th degree polynomial. The fundamental theorem of algebra says that there's going to be 7 solutions or 7 zeros. Some of them might be complex and we might have some multiples, but there's going to be 7 solutions. Descartes' rule of signs is a method of determining the maximum number of positive real solutions and the maximum number of negative real solutions. And what we do is we just look at the coefficients and we count the sign changes. It's actually fairly easy to use. My coefficients here are 1, 1, negative 1, negative 1, negative 1, positive 1, negative 1. So let's see how many times the signs change. This is positive to positive. That's not a change. Here's a change to a negative, so that's 1. Stays negative, stays negative. And here's another change to a positive. That's our second sign change. And then positive back to negative is 3. So there are 3 sign changes. So this means there's going to be possibly 3 positive real solutions, or 1. I can subtract even multiples. So let me write down that conclusion. So my conclusion about this polynomial is that there's 3 or 1 positive real zeros. The maximum is 3, but the good news is there's definitely 1 real zero, and so I'm going to probably look pretty hard to find that. Descartes' rule of signs also tells us the maximum number of negative real zeros, and in order to do that, we get a new polynomial f of the opposite of x. So here's the f of the opposite of x. When we put the opposite of x in for x and raise it to the 7th power, we will get the opposite of x to the 7th. When we put the opposite of x, which does mean negative 1 times x, in for x here and raise it to an even power, it's going to stay positive. When we put it in here, it's going to stay negative. Notice there is no x to the 5th term. That's okay. You don't have to have every degree. When you put the opposite of x in here, this will change to a positive x cubed. This is going to remain negative x squared. This is going to become negative x, and this is going to become negative 1. So now we're considering this polynomial. So this is the polynomial I'm looking at, and I'm going to count the sign changes in this polynomial. Negative to positive, there's a sign change. And positive to negative, there's a second sign change. Negative to positive, that's a third sign change. And then positive to negative is a 4th sign change. And then there's no sign changes here. So it looks like there's 4 sign changes. So we conclude that there's a maximum of 4 negative roots, or less than this by an even multiple. So let me write that conclusion. So here are our conclusions about the original polynomial. There's 3 or 1 positive real zeros, and the number of negative real zeros is 4 or 2 or 0. It might be that there won't be any negative real zeros. So the minimum case would be 1 positive real zero and no negative real zeros, which means the other 6 zeros would all be complex. One thing about complex solutions is they always come in pairs. There will always be an even number of complex solutions. Okay, now let's look at the rational root theorem. The rational root theorem is going to give us possible rational roots. Now, roots for a polynomial might be rational, which means a fraction like 2/3, or even a number like 5, because 5 is rational because it's 5 over 1. They might be rational. They might be irrational like the square root of 2, or they might even be complex like 2i or I root 3. The rational root theorem only gives us possible rational roots. So our polynomial is going to be of this form: a sub n x to the n plus a bunch of terms in between through a constant. For example, 0 equals 2x to the fourth minus 7x cubed plus x squared plus 7x minus 3. To use the rational root theorem, you only use the leading coefficient, which is 2, and the constant, which is negative 3. In this case, the leading coefficient is an, and the constant is a0. The possible rational zeros are of the form p over q, where p, looking over here on this left-hand side, and then we'll look at the example in a minute, p is a divisor of the constant, and q is a divisor of the leading coefficient. This should be an. Let me fix that. There we go. So let's look at our specific example. P, which is the numerator, could either be plus or minus 1 or plus or minus 3. We're talking integers here. Q are the factors or divisors of 2, which are plus or minus 1 or plus or minus 2. So if we put all the combinations together, we get the following possible rational roots. Plus or minus 1, which comes from 1 over 1. Plus or minus 3, which comes from 3 over 1. Plus or minus 1/2, which comes from 1 over 2. And plus or minus 1/3, wait a second here. That's not right. This is incorrect. There we go. Now it's correct. These numbers go on the top, and these numbers go on the bottom. So the last possible rational root would be 3 over 2. So now we are ready to take a look at our final video to see how synthetic division works, where we can test out these possible rational roots and find out which ones really are solutions. My name is Jim Olson. Stay tuned for the next video. Have a great day.